Okay, everybody, this is the audio to accompany the video I posted called 3.1 Finish. So you might want to try, I don't know, watching this on your Chromebook and listening to the other file on your phone. You guys will figure it out. You're smarter than I am. All right, I'm going to start that video and narrate along with it in about 3, 2, 1, and now. All right, so as we move on to example 5 in our 3.1 notes, things are starting to get a little bit tougher now. It's the same basic concept we did in example 4, except now the function is a lot more complicated. It's 2x squared plus 3x minus 5. And just like last time, we're using the definition of the derivative, but here we're finding dy dx. We're using Leibniz's notation right now because the original function was called y rather than f of x. But it's still a definition of derivative problem. So the formula for that isn't really going to change. Anytime the derivative says we have to use the definition of derivative, that means we have to do a limit and no shortcuts. So this formula is the same one we've been working on for the last couple days. Limit as h approaches 0 of f of x plus h minus f of x all over h. It's a little weird this time because there isn't an f of x to speak of, but you guys will figure out what's going on right there with the y instead. So since this one's a lot more complicated than the last one that we worked on, we're going to have to pay attention here and try to stay organized because the numerator of this can get really, really difficult. And there's a lot of simple little algebra mistakes that are going to be very easy for us to make if we're not careful and patient and try to avoid those. So the best piece of advice I can give you guys is to try to use brackets as much as possible in your numerator to help yourself stay organized. So the f of x plus h is what we need to focus on first. And since the original function here is 2x squared plus 3x minus 5, we're going to replace all of those x's with the binomial x plus h. So I'm going to use a red set of brackets here to start my numerator. Everywhere there was an x, we replace it with an x plus h. So we have a 2 times x plus h quantity squared plus 3 times x plus h and a minus 5. Now that takes care of the f of x plus h, so we'll close that off with another bracket. And just showing the same thing going on up here. A minus sign comes next, and now the f of x, the second part of the original numerator, I'm going to put in a green set of parentheses here. And again, that's the easy part. F of x is just the original function we were given unchanged. 2x squared plus 3x minus 5. The denominator is just going to stay h, and this is the limit we now have to evaluate. I'd love to tell you guys to think about plug and chug, but it doesn't work here and it never will, because you're always taking a limit as h approaches 0, and your denominator is always h. So what we need to look for next is some algebraic simplification in the numerator that might make this limit something that we can evaluate. So we're going to stretch things a little bit right here, and if you need to show this in 2 steps, you can, but I'd like for you guys to push yourselves a little bit here. We need to try to expand this 2 times x plus h quantity squared. Now, you guys should be able to do the binomial squared mentally, and we're also going to distribute the 2 in there at the same time. So with a little bit of practice, I think you guys will get the hang of it. All right, the first term of x plus h quantity squared is going to be x squared, but distributing the 2 into that is going to get us a 2x squared. The second term would have been a 2xh. Distributing the 2 there gets us a plus 4xh. And the last term was h squared, multiplied by 2 is going to get us a plus 2h squared. Okay, that takes care of the first term. Now the second one, we just need to distribute the 3 into the quantity x plus h, so that'll get us a plus 3x plus 3h. And nothing to do with the minus 5, so we'll just write it out. And the only thing to worry about now from the numerator here, and it's silly, but people do forget it, is to distribute that negative inside the original f of x polynomial. So that's going to get us a minus 2x squared, minus 3x, and a plus 5. Yes, that sounds silly, but trust me, people get blinded by the light and are so worried about the hard stuff, a lot of times they mess up the easy things. Still an H on the bottom. Now, what we'll notice is that we have a lot of terms here. In fact, 9 terms in the numerator in this example. But what's going to happen here, and what's going to happen every single time we do this, is that all of the terms in the numerator that don't contain an H are all going to cancel out with their opposites. Let's take a look at that. We see a minus 2x squared here in green, and a positive 2x squared to the left there in red. They cancel each other out. Then a minus 3x and a plus 3x. Those are gone. And at the very end, we see a plus 5, and a minus 5 comes before that. Those will cancel each other out as well. So you'll notice then, guys, the entire f of x polynomial is gone. And that should happen every time that you do this. Okay, so what's left over? Once you get the hang of this, you can probably skip 1 or maybe 2 of the steps that I'm about to show, but for now, let's try to be thorough about it. You'll notice that all of the terms we have left, there are 3 of them in the numerator, all contain an h. That works really well for us. So we're going to go ahead and we're going to rewrite this limit because we're not ready to put a 0 in for h just yet. And we're going to go ahead and write what's left over, 4xh plus 2h squared plus 3h all over h. And now I think you guys probably see what's coming next. We're going to factor out that h. And again, this is a step I would normally skip if I was doing this on my own, but just to show everybody exactly what's happening, let's spell it out. The h comes out, leaving us with a 4x plus 2h plus 3. And now, what we've been waiting for to happen finally did. The problematic factor of the denominator now cancels out. So again, I'm sure you could look at this right now and tell me what the answer is, but we'll go ahead and let the h become 0 since the function is now continuous at that value. So we have a 4x plus 2 times 0 plus 3. That middle term drops out, and here we go, everybody. The derivative of y with respect to x is equal to 4x plus 3. Now, those of you who remember your shortcuts from pre-calc, which is all of you, probably looked at this original function here 5 minutes ago and said, I bet that derivative is 4x plus 3. And sure enough, you were right. But this is how we get that answer using the definition of the derivative, which the directions will occasionally require us to use. Now that's really about it for new content here within 3.1, but I thought it would be a good idea this year to spend a little bit more time talking about how the book sometimes uses some different versions of the definition of the derivative from what I use, and I don't want to confuse you guys too much. So we're going to talk about 3 different ways of essentially obtaining the same answer. The first one here, everybody, is going to be, well, what I'm just calling our version, the way I prefer it here. And it's important to understand not just the formula that comes on the right with the limit and the difference quotient, but also that this formula begins with f prime of x equals. It's very important to understand what it is that you're finding before you just dive in and start using a formula. So this is the one we've been talking about since last week, everybody, that f prime of x, what we call the general expression for the derivative, which we can then evaluate to find the value of the derivative at specific values, is equal to a limit as h approaches 0 of f of x plus h minus f of x all over h. I don't think we need to talk too much more about that. That's what we've been doing for a while. But the second thing I wanted to discuss with you guys here is what your author tends to do, the book's version of derivative at a point. Now we'll get to that in just a moment, but this does not give us a general expression for the derivative. It doesn't give us f prime of x. It gives us the specific value of the derivative at a particular value called a, which is eventually going to be our point of tangency. So it's really the same diagram we were talking about last week. It's just that the notation is a little bit different. Instead of calling that point x f of x, we're now calling it something specific, a f of a. I don't know what I was saying here when I did this before, but I'm sure it was brilliant. All right, any day, Mr. Fontana. Here we go. Okay, so in this notation, we're still letting h represent the horizontal distance between these 2 points of sequency. That hasn't changed at all. So if we do that, this second point has an x-coordinate of a plus h. And as we shoot that up to the curve and over to the left, its y value is going to be f of a plus h. So really no change in notation right here in terms of how we name things, just that that first point was called a rather than x. So with those two pieces of info in mind here, you're going to see that this formula really hasn't changed a whole lot. Other than the fact that in the last version, we were finding an expression for our derivative, f prime of x, which is what we're going to call the general derivative. That usually gives us an expression in terms of x that we can evaluate at any given value of a. But here, we're not finding f prime of x, we're finding f prime of a, which is what we call a specific derivative. It tells us what the slope of a tangent or an instantaneous rate of change actually is when we know the a value in question. Okay, so back to it. It's going to be pretty much the same idea as before. It's still a limit, and we're still taking h and letting that approach 0. But of course, things change just a little bit now. As we go to lay out our numerator, our ending y value, instead of being f of x plus h, is now going to be f of a plus h. We're then going to subtract f of a, which was our starting y value. And down on the bottom, we would be taking a plus h minus a, but as I think you can see, those a's are going to cancel out immediately and leave you with an h. So this is the book's version of this formula, guys. It's just important to understand that instead of f prime of x, we're finding f prime of a. No, I didn't want a square there. I wanted a rectangle, and that thing was in my way. So let's try that again. There we go. That looks much better now. So that's the formula for the specific derivative at x equals a. And the book, everybody, is going to call this equation 1. So if they reference that in the homework at all, this is the equation that they're talking about. Now, for my money, everybody, I never use this equation right here. It's usually faster if we just need to find the value of a derivative one time, but if you ever needed to do that for multiple x values on the same function, you're usually much better off here going with our version, which gets you the general derivative, and then evaluating that as many times as you need it to. So I would always prefer our version over the book's version. But there's another one out there that they call the alternate version of derivative at a point that actually is somewhat useful, and I've seen show up and be needed on a couple of AP questions, so I want to walk you through this one as well. Again, the diagram looks pretty much the same. We have a curve, we have a red dot that's our eventual point of tangency labeled a, f of a. But now, this one's just a little bit different in the way that we label what comes next. That second point of sequency, which we have in a green dot right there, well, this time we're not going to use h at all as the distance between those. We're going to ignore that, and instead of defining the second point in terms of the first, we let the second one just be its own variable. So we'll call that x, which heretofore is unrelated to a, and its y value is, you guessed it, f of x. So with all this in mind, let's take just a moment here and let's consider the secant line that passes through the red dot and the green dot. So our formula for slope of a secant is just change in y over change in x. So we're going to go with f of x minus f of a for change in y, and for change in x on bottom, just an x minus a. So hopefully that notation looks familiar. It's pretty similar to what we were doing back in chapter 2, although there we were usually using a b and an f of b. So now if we want to take that secant and turn it into a tangent line, which again is the same thing as finding the derivative of our function evaluated at a, well, I think you guys get the joke right here. What we're going to have to do in order to do that is take that second point of sequency and slide it down the curve so that it's going to move closer and closer to the original point. So it's a limit, but as what approaches what? So what we want to see happen here is this second dot here that was at x f of x, I don't know why that box is there, we want that dot right there to slide further and further down the curve so that our secant becomes more like a tangent. What we really want is for x to move from right to left until it gets closer and closer and closer to the value of a. So we're taking a limit here as x approaches a. But the good news is everything else is exactly the same. So now we finish this up with the same formula we just wrote down for the slope of a secant. F of x minus f of a all over x minus a. And that formula right there is what the book calls the alternate definition for derivative at a point. So once again, it's a formula not for f prime of x, but for f prime of a. And your book calls this, oh, sorry everybody, a limit as x is approaching a becomes the important thing as opposed to a limit as h approaches 0. And here we go. This is what your book calls equation 2 in case that one shows up anywhere. So you might need to know that as well. Okay? Now, I thought it would be a good idea before we wrap things up over here to take a look at what that alternate definition of derivative at a point looks like in action. And if I were going over this with you guys actually in the room to show you that this is something that's really, really cool, that just kind of seems to work out on its own, I was going to ask you guys just to shout out some numbers for me. But since I'm doing this alone and you're not there, I'll just pretend I was asking for random numbers from the gallery. So what we need here, everybody, is a value of a that's going to go inside that set of parentheses there, where we're going to evaluate our derivative, and we need a function here on which to try this. So let's take a look at what's going on right here. So we're going to go ahead and just choose a random a value of 3. And for making up a function, I thought we'd stick with a quadratic, but make it one that's a little bit more complicated than it needed to be. So how about something like a 5x squared, minus a 2x, and then maybe a plus 7. Seems like a good random, not too nice quadratic trinomial. Okay, so we have our function, we have our value of a, that's 3 right here, and we're going to try to figure out the value then of f prime of 3. We're going to do that using the alternate definition of derivative at a point. Remember, everybody, that a is actually representing the x value of your point of tangency. So here we go. Using equation 2, the formula we just wrote down here is that f prime of a, which in this case is 3, blah, blah, blah. Okay. Here we go. Is equal to a limit, not as h approaches 0, but as x approaches a. So in this case, x approaches 3, of, up in the numerator now, f of x minus f of a. So the f of x should be the easy part. That's the original function, unchanged. 5x squared minus 2x plus 7. But then from f of x, we now need to subtract the value of f of a. Well, since a is 3, f of a is going to be f of 3. So we'll plug that 3 back into the original function directly above where I am right now, and here we go. 5 times 3 squared is 5 times 9. That's going to get us 45. Minus 2 times 3 is a minus 6, plus 7 is going to get us 46 for the value of f of 3. And since what we needed in that second set of parentheses was f of a, the 46 is the number we put in there. All over the binomial of x minus a, which in this case is going to be x minus 3. And now this is a limit that we need to try to evaluate. Obviously, plug and chug isn't going to work because we're going to end up with 0 on the bottom. But the cool thing about this, one of the things that really makes me smile about doing this section and think this stuff is really cool, is this. That quadratic trinomial was just completely made up off the top of my head. And I think you guys know that most of the time, if you were to just randomly pick coefficients in a trinomial, the odds of it factoring are actually really, really slim. That 46 seemed like a weird random number too, but something cool happens here and will happen every time we do this. Let's take a look. This is now a limit as x approaches 3 of 5x squared minus 2x, and then we have a plus 7 minus 46, which is going to get us a minus 39 all over an x minus 3. Now, it seems really unlikely that this random trinomial up on top would factor, but the cool thing about it is it does. And not only does it factor, this is kind of a tough one to factor just by looking at it, but a trick we talked about back in chapter 2 shows up again. The denominator of x minus 3 is guaranteed to be one of the factors of the numerator. Now, I don't want to just assume that completely, but I am going to run with it for right now, and we'll come back and check ourselves with FOIL. But the only way this is a limit we can evaluate is if one of those factors is also x minus 3. So now let's kind of do FOIL in reverse here and see if we can figure out what that first trinomial here is going to be. A term right here needs to get multiplied by x to give us 5x squared. So 5x is what we need. Now if we look at constants, the term that goes right here has to be multiplied by negative 3 to equal negative 39. Positive 13 is what we need right there. But again, I don't want to just assume this worked, so let's check it with FOIL. First, outer, inner, last on the two binomials and make sure it works. The 5x times the x gives us the 5x squared we needed. The outer product, 5x times a minus 3, is minus 15x. The inner product, 13 times x, is a plus 13x. And when we combine those two quickly before they fade away, that gets us the negative 2x that we needed for our middle term. And I think we can see pretty quickly the last product works as well. The positive 13 multiplied by the negative 3 is going to get us the negative 39 we need. So sure enough, everybody, it factors. And now the entire factor of x minus 3, top and bottom, cancels out, leaving us now